to our professor, Dr. in Engineering Edgardo Uvas. Good day, sir, and welcome to my video presentation for the assessment numbers 2 and 3 and advanced statistics. My name is Gilbert F. Sagaral, BSed for Mathematics. Before this semester ends, we are tasked to choose a topic from measures of association to discuss through video presentation as partial requirement of the subject in statistics. The measure of association refers to a wide variety of coefficients that measures the strength and direction of the relationship between two variables. Measure of association provides a means of summarizing the size of the association between two variables. It comprises a class of descriptive statistics that quantify a relationship between variables. Association exists if the distribution of one variable is related to the distribution of the another variable. Most measures of association are scaled so that they reach a maximum numerical value of 1 when the two variables have a perfect relationship with each other. They are also scaled so that they have a value of 0 when there is no relationship between two variables. Tests of significance are also provided for many of the measures of association. These tests begin by hypothesizing that there is no relationship between the two variables and that the measure of association equals 0. The researcher calculates the observed value of the measure of association, and if the measure is different enough from 0, the test shows that there is a significant relationship between the two variables. The choice of the proper measure of association is based on, among other things, the characteristics of each of the variables involved. One way to determine that whether there is a statistical relationship between two variables is to use the point-by-serial correlation coefficient. A point-by-serial correlation coefficient is used to measure the relation that exists between one continuous or interval or ratio scale variable and one natural dichotomous or nominal scale variable. When you say continuous, in our previous statistics, it may have a certain decimal, not exact, not discrete. While dichotomous, in other words, binary, it may point-by-serial correlation coefficient measures the strength of association of two variables in a single measure ranging from -1 to +1, where -1 indicates a perfect association, perfect negative association, +1 perfect positive association, and 0 indicates no association at all. The higher the value of the point-by-serial correlation coefficient, whether it is positive or negative, is the stronger relationship between the two variables. To adequately explain the point-by-serial correlation coefficients, we will need to address 3 questions. What is point-by-serial correlation? And how is the point-by-serial correlation coefficient related to other correlation coefficients? How is the point-by-serial correlation coefficient calculated? As James Dean Brown on 1988 defined it, the point-by-serial correlation coefficient is a statistic used to estimate the degree of relationship between a naturally occurring dichotomous nominal scale and the interval or ratio scale. When you say naturally occurring dichotomous nominal scale, it is a kind of variable which has exactly 2 categories or can be split into 2 categories. Let's say, for example, a researcher might want to investigate the degree of relationship between gender, or that is being male or female, which is a naturally occurring dichotomous nominal scale, or a binary nominal scale. And achievement in mathematics is measured by scores. We know that scores is an interval scale in the scale of measurement of variables on the final examination. How is the point-by-serial correlation coefficient related to other correlation coefficients? To simply put it, we will look for the types of scale, the variables involved in a certain study. If the 2 variables involved are both scales or are interval or ratio, we can use the correlation coefficient Pearson's product. But if both scales are ordinal, we can use the Spearman's rank order. or the Spearman rho. Both scales are naturally dichotomous or nominal. We can use phi correlation coefficient. If both scales are artificially dichotomous, when you say artificially, say for example, we want to split a variable into two categories. For example, in CBSUA, we determine the grade by by 1, 2, 3, 4, and 5. We can split it from 1, 2, 3. We can categorize it as passed, and 4 and 5 as failed. That is artificially dichotomous or binary. Point by serial correlation coefficient. If one scale is naturally dichotomous, let's say for example gender, we have exactly two categories, which is male and female, and one scale is interval or ratio. In biserial, one scale is artificially dichotomous and one scale is interval or ratio. We already explained what is artificially dichotomous and the difference of it from natural dichotomous. In gamma correlation coefficient, one scale should be nominal and one scale should be ordinal. To calculate the point by serial correlation coefficient, we use the following formula, which is R sub PBI, or R. We use R like Pearson product because point by serial is a special case of Pearson product correlation moment correlation coefficient. R sub PBI is equal to the difference of M sub P and N sub Q divided by standard deviation, or S sub T, times the square root of the product of P and Q, where R sub PBI is the point by serial correlation coefficient, M sub P is the mean for the entire test of the group that received the positive dichotomous variable, and M sub Q is equal to is the mean for the entire test of the group that received the negative dichotomous variable. S sub T is standard deviation for the entire test. P refers to proportion of cases in the group that received the positive dichotomous variable, and Q is the proportion of cases that in the group that received the negative dichotomous variable. Suppose you want to determine if a significant relationship exists between the gender of BS and for mathematics students and their scores in the final examination. We have your scores for males 90, 85, 78, 73, 93, and 79. For female, 85, 79, 89, 90, and 95. Our solution is from the above statement, we can say that our naturally dichotomous variable is the gender, because we can split it in exactly two categories, male and female. And the continuous variable is the score. For us to be able to present the data in an organized way, we can arrange it in a tabular form like this. But before that, we should state our null hypothesis. There is no significant relationship between the gender of these and for mathematics students and their scores in the final examination. We can say that our null hypothesis is equal to zero association. The relationship between gender and score, dichotomous versus interval, is the table for our data. I assigned letters for the student column, and the test score, or assigned variable X, gender, and the last column is the the difference of test score and the mean of the sum of test score. From this data, we can proceed to our calculation. Now, we can use the formula given a while ago, which is point by serial correlation is equal to the mean for the entire test in the group that received a positive dichotomous variable minus the mean for the entire test that received negative dichotomous variable divided by the standard deviation of the entire test times the square root of the product of the P and Q, or the cases of the proportion of the entire entire test. First, we need to get the mean for the group that received the positive dichotomous. Traditionally, uh, other researcher used 1 and 0, or they assign 1 for the positive group and 0 for the negative group. But here I only use the male and female group. The score of the males from our data is 90, 85, 78, 93, 79, and 79. To get the mean of the male group, we only add these scores and divided by the number of males. We have 90 plus 85 plus 78 plus 93 plus 79 is equal to 425 divided by 5 is equal to 85. The same for the female group, we get their scores and add, then divide by the number of females, which is equal to 438 divided by 5 is equal to 87.6. To get the cases in proportion, we just count the number of male, which is 5, divided by the total number of the respondents. We have here 5 males divided by 10, which is equal to 0.5 or 1/2. The same as for the female group, 5 over 10 is equal to 0.5. In order for us to find the value of the point-based correlation coefficient, we need first to get the standard deviation for the entire test. In our previous statistics, we use this formula to find the standard deviation. Standard deviation for the entire test is equal to the square root of the summation of x minus x bar, or the mean, raised to 2 divided by n minus 1. N is the number of cases. For us to be able to get the total summation of x minus x bar square, we get this in the last column of the table. We have here the total value is 334.1. We substitute it in the formula, and n is the number of cases. We have here 10 cases. 10 minus 1, 9. When we divide 334.1 divided by 9 is equal to 37.12. We get the square root. We have here approximately equal to 6.09. And this is our standard deviation. We now use the formula. We just substitute what value we got from this computation. Our m sub p is equal to 85 and our m sub q is 87.6. Get the difference. We have negative 2.6 and our standard deviation is 6.09. Get the quotient of these two, then multiply to the square root of the product of p and q, which is 0.25, square root na ay 0.5. And the product of these two is negative 0.2134, which is approximately equal to negative 0.21. Since our point-based correlation coefficient value is negative 0.21, which is very close to 0, we will know that 0 has no association at all between the two variables. Therefore, we fail to reject the null hypothesis, which is there is no significant relationship between the gender of BSN for mathematics students and their scores in the final examination. From the result of our computation, we can show it in a diagram. From 0 to negative 0.21 is very close to 0. But if we get a higher value of our point-based correlation coefficient, for let's say for example negative 0.75, which is very near or very close to negative 1, a perfect negative correlation. Since our value is negative 0.21, which is very close to 0, no relationship at all between the two variables, we conclude that based from our decision, we can conclude that the relationship between the gender of BSN for mathematics students and their scores in the final examination is very weak. Thus, we are not advised to conduct t-test anymore. Thank you, and that's all.